Alright guys, welcome back to another lecture. Section 2.6, we're going to be finding the inverse of a square matrix. And when I say inverse, I mean the multiplicative inverse, not the additive inverse. Prerequisites are easy. You just need to be able to do elementary row operations. We're going to get a lot of run out of just being able to do these simple elementary row operations. That's going to be the entire semester. So, why? What's the motivation behind this? Well, what we're really trying to do is we're really trying to build algebra, okay? We have addition, we have subtraction, we have multiplication. You can add, subtract, multiply matrices. Sometimes sizes have to line up. There's no such thing as division. Like it doesn't make any sense to say A divided by B if A and B are two matrices. But if I have some sort of algebraic problem, let's say matrix A times some vector x, I don't know what it is, plus b is equal to c. Again, a, b, and c are matrices. Then as long as these operations are defined, it makes sense to subtract b, right? So I can say a times x is equal to c minus b. That all makes sense. The problem here is if I'm looking to solve for this variable valued vector x here, I'd like to, well, for lack of a better word, move that a. I want to shove that a over to the right-hand side of my equation, but there's a problem. I can't divide it, right? Well, we're going to define the inverse of our matrix classically, okay, which is to say we define multiplicative inverses as objects which multiply together to give you the identity. So, for example, the multiplicative inverse of 7 is 1/7, because 7 times 1/7 gives me 1, and 1 is the identity for multiplication. Now, if you remember back to our lecture on matrix algebra, we talked about the identity as far as matrix multiplication is concerned. We call it I, okay? But the size is gives rise to its full name. So I, in whatever shape form you want, is a square matrix with ones along the diagonal and zeros everywhere else. I gave the formal definition in the previous lecture. Okay? So this one is I2. This one is I3. Okay? And when we say I, we mean whichever one is relevant at that point in time, right? So if I had a matrix A, right? I had a matrix A and another matrix which I'm going to call giant K for a second. If the product of those was I, any I2, I3, doesn't matter, then what I'm going to say is I'm going to say that K is the inverse for A. Like 1/7 is the multiplicative inverse for 7. And you'll notice that if you apply both of those, multiply something times 7, then multiply it by 1/7, you have no change, right? That's what we're looking to do, okay? And so at that point in time, what I would say is that I would say that K, we'll replace that with this symbol. We have A, and we'll put a little -1 exponent there to represent this is A inverse. This is the inverse multiplication matrix for A, okay? And now, suppose this exists. So if I actually have the matrix that creates this, then I can do the following with my algebra. Okay? What I can do is I can left multiply both sides of my equation. Got to remember, multiplication's not commutative, right? So if I left multiply by A inverse on the left-hand side, I have to left multiply by A inverse on my right-hand side. Okay? And so what I get now is I get this simplification on the left. I get that A inverse times A, well that's I. Okay? Which I? I don't know, whichever one, I sub n. Okay? And then the product of I sub n and that vector x, well it's just x. Again, I is the identity. It doesn't change. And this allows me to solve, right? So what I'm doing here is I'm building the concept of algebra, the ability to operate with these things. Now, I did mention something, and it bears repeating. I said, suppose this exists. All right, well, the implication in that statement is what? That not everything has a multiplicative inverse. And this is true with basic numbers as well, but it's a little bit more narrow. See, with basic numbers, with real numbers, the only number that doesn't have an inverse is 0, right? Because it's trivial. The inverse for 12 is 1/12. The inverse for 7 halves is 2/7. Again, you take a reciprocal, right? There's no reciprocal for 0, so it doesn't work. Here, it'll be a little bit more complicated, but we do in fact have many, many, many more instances when dealing with matrices of objects that do not actually have a multiplicative inverse. Now, we're going to cover what those are and how you determine it in another couple sections in section 2.8. For right now, I'd like to show you the process by which you can find an inverse. And you can do this process whether or not you know whether the matrix has an inverse or not, because if it doesn't, then the process will fail. So we're going to be okay. What we're going to be using is something called the Gauss-Jordan technique for creating the inverse of a matrix, or finding the inverse of a matrix. Okay? Now, it's important that we're only considering square matrices, so we'll restrict ourselves to those. Let's see. So I'm going to take an example out of the book just to make sure I don't accidentally make up something that doesn't have an inverse. That would be awkward. Okay? Let's say my matrix is 1, 1, 3, 0, 1, 2, 3, 5, negative 1. So this is a 3 by 3 matrix. Okay? So what I'm looking for another 3 by 3 matrix that if I multiply it by this one, I get the identity matrix I3. Okay? All right, here's the process by which we're going to do that. We're going to create what's called an adjoint matrix. Okay? Basically, I'm going to take A and I'm going to glue a copy of I3 attached to it. So, like so. So here's A, 1, 1, 3, 0, 1, 2, 3, 5, negative 1, right? And I3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. And I'm going to glue these two things together. Now, the way we sort of notate this is, I'm just going to put a little vertical line here, just to sort of remind myself, these are two separate matrices. Okay? Now, hopefully you're asking, why would we ever do this? Well, in a minute, I'm going to do a lot of elementary row operations to A. But I would like to do all of the same operations to I3 as well. Okay? So if, for example, I do A13 negative 3 to A, then I want to do A13 negative 3 to I. Well, if I just glue them together, then I can do everything all at once. Right? This saves me some time. So now the process is simple. I'm going to carry over all my elementary row operations, but my focus is going to be here on the left. I would like to put this matrix into reduced row echelon form. Okay? Again, reduced row echelon form. That means I not only want lead ones, again, I want them staggered. I also want zeros below and above all my lead ones. Okay. So the first thing I'm going to do, pivot, that needs to be a 1. It is. Yay for us. I'll use that 1 to kill the things below it. And I just have that 1, 3 down there. So let me go ahead and do A1, 3, negative 3. That's going to kill off that 3. Let's see what we get. So with A1, 3, of course, rows 1 and 2 don't change. So row 1 will still be 1, 1, 3, 1, 0, 0. And row 2 will be 0, 1, 2, 0, 1, 0. Okay, now let's see what happens in row 3. Okay, again, take this value, multiply it by negative 3, and then add it to the value that's already there. 1 times negative 3 plus 3 gives me 0. 1 times negative 3 plus 5 gives me 2. 3 times negative 3 is negative 9, plus negative 1 is negative 10. Okay. 1 times negative 3 plus 0 is negative 3. And the remaining two are 0 times negative 3. Well, add that, you still have a 0. And 0 times negative 3, that's 0. Add that to the 1, you still have a 1. Okay, fantastic. Now, again, I'm looking to go to reduced row echelon form. Okay, so I move down, I move to the right, I pivot. I want that to be a 1. It is a 1. Hooray for us. Okay, so I'm going to use this one, my new pivot one. I'm going to kill the values below and above it. Okay, so I want to use this one here to make that a 0 and make that a 0. We always work left to right. Yes, always left to right. So I made this a 1, kill the things below it, down to the right, pivot, kill the things above and below it. I'll move down and to the right and then kill the things above and below that. So to use this one, to annihilate those two values, we need a 2, 1, negative 1, and we need a 2, 3, negative 2. Okay, so that will use this one to turn that into a 0 and use that one to turn that 2 into a 0. Let's see what we get. Okay, so with these two operations, row 2 will not change. It's 0, 1, 2, and then 0, 1, 0. All right, let's see what happens with the rest of the matrix. A2, 1, negative 1, take this value, multiply it by negative 1, and add it to the value in the first row. So 0 times negative 1, 0 plus 1, that's still a 1. 1 times negative 1, that's negative 1 plus 1 is a 0. Okay? And these were, we knew how those were going to come out, right? 2 times negative 1 is negative 2 plus 3 gives me 1. 0 times negative 1 plus 1 is a 1. 1 times negative 1 is negative 1. Add that to that 0, you get a negative 1. And 0 times negative 1 is 0. Add that to the 0 that's already there, and you get a 0. All right, how about A2, 3, negative 2? Fine. Again, 0 times negative 2 plus 0 is still a 0. 1 times negative 2 plus 2 gives me a 0. 2 times negative 2 is negative 4 plus negative 10 is negative 14. Okay, here we go. 0 times negative 2 is 0 plus negative 3 is negative 3. 1 times negative 2 plus 0 is negative 2. And 0 times negative 2 plus 1 leaves me with a 1. I'm almost there, right? I'm almost there. What I need to do, and I'm running out of room here, so what I need to do is I need to take that new value, I need to pivot, move down and to the right. Okay, so move down to the right. And I need to turn this into a 1 and then use it to kill the two values above. Now I'm running out of space. I only have room for one more operation here. So I'm going to go ahead and do something that I really don't like doing. I'm going to reduce this row. There's only one way to turn this into a 1. I have to multiply this row by negative 1/14. Okay? There's no rows below it to interact with, so I can't permute, I can't add. Okay? I'm going to tack on, do not do this in your own work. I'm going to tack on multiply row 3 by negative 1/14. Now those changes will turn this into a 1. I'm going to put this in a different color so we know that I did this afterwards. This will become negative 3 times negative 1/14 is, well, 3/14. Negative 2 times negative 1/14 gives me positive 1/7. And negative 1/14 times 1 gives me, well, negative 1/14. And now I'll use this 1 to annihilate the two things above it. Now notice the thing on the right is getting ugly, but there's no control over that, right? Use the 1, kill those two things. I need A31 negative 1 and A32 negative 2. And that should actually finish this off, right? Remember, the purpose was to take the left-hand part and turn it into reduced row echelon form, right? All right, let's see what happens. So remember, row 3 is not going to change. 0, 0, 1. I've got 3/14, 1/7, negative 1/14. Okay, so A31 negative 1. Take the value from row 3, multiply by negative 1, add it to row 1. I get 1, 0, 0. Okay? Negative 3/14 times negative 1 is negative 3/14 plus 1 gives me 11/14. 1/7 times negative 1 plus negative 1 gives me negative 8/7. Negative 1/14 times negative 1 plus 0 is positive 1/14. All right, row 2. Again, A32 negative 2, take the value in row 3, multiply by negative 2 and add it to the value that's already there. I get 0, I get 1, I get 0. Okay? And now let's actually work these. Negative 3/14 times negative 2 is negative 3/7 plus 0 is negative 3/7. 1/7 times negative 2, negative 2/7 plus the 1, 5/7. Negative 1/14 times negative 2 is positive 1/7 plus 0, 1/7. Okay. So notice what's happened here. With all these operations, I started with A on the left and I3 on the right. And now I have I3 on the left. Well, because this has an inverse. I should point out that this process fails if the left-hand side does not become I3. And the only way that can happen is if it has rows of all zeros. Okay? If that happens, then there is no inverse, so you're done, right? But this ugly thing right here, if you find it, that's A inverse. If you multiply this matrix times this matrix, you get the identity. You really should try that on your own. Okay? You really should try. Take A, and you can left or multiply it by A inverse. Doesn't actually matter. We got A inverse is 11/14, negative 8/7, 1/14, negative 3/7, 5/7, 1/7, 3/14. This is hideous. 1/7, negative 1/14. So you should try that on your own. Okay, just multiply those things together to verify they do actually have an inverse. So now ask me, are they all going to turn out this ugly? Well, think about the example I gave you with real numbers. What was the multiplicative inverse for 7? Wasn't it 1/7? The multiplicative inverse for 19 is 1/19. Yeah, it kind of makes sense, right? Now, this won't always happen. There are a few examples that are in your book where you have a nice matrix, a matrix with nothing but whole numbers, and its inverse happens to have nothing but whole numbers. But that is very, very rare, okay? That is few and far between, and that only happens if the determinant of that matrix happens to be 1 or negative 1. But we'll talk about determinants in chapter 3. Okay. Okay. So, yeah, you need to practice this. You will need to be able to find the inverses of matrices, and nothing is going to be better than you just working a few. I want to talk about some of the properties of the inverse. This is a pretty quick lecture, so let me talk about some of those properties. But again, try some of these. You have homework already assigned to you. and you'll get the hang of these. Just still doing elementary row operations. Okay, so suppose you have a couple matrices that you know are invertible, right? That you know their inverses exist. So let's say, suppose A and B are invertible matrices. Okay, so I know their inverses exist, right? They're not zero factors. Then the inverse of the inverse would have to be itself, right? This makes sense, right? If I define the inverse of something as the thing I multiply it by to get the identity matrix, then this is asking me what's the inverse to A inverse. Well, it has to be A. They're paired, right? A and A inverse are the two things you multiply together. So in that way, we can sort of think about these things as canceling one another. Okay. The second property, if A times B is invertible. Okay. So again, I know A is invertible. I know B is invertible. If those two things are invertible, their product is guaranteed to be invertible. Okay? And I can even tell you what the inverse is. And the inverse is the product of B inverse and A inverse. Okay? If you think about it, what would happen if I actually multiplied them? Okay? So if I actually multiply AB times B inverse A inverse, well, matrix multiplication is not commutative, so I can't shuffle these around, but it is associative. Okay? And so I can rewrite it like this. Same order, right? The same actual order, but I'm rewriting which of these multiplications gets done first. B times B inverse, however, is just I. And I times either one of these matrices are themselves, which simplifies down to A times A inverse, which we know is also I. Yeah. So this is the inverse for this one, right? So again, if A is invertible and B is invertible, then I know that B inverse A inverse, this is the inverse for AB. Okay? And it turns out that transpose also works very nicely with inverses. Okay? Seems like it should, right? Remember from the very first section in chapter 2, we defined transpose. A transpose is the matrix you get from A by just swapping all the rows and columns. And it seems like if you swap all the rows and columns and then you want the inverse, shouldn't you just swap all the rows and columns in the inverse you already had? And that's true. Okay? The inverse of A transpose is just the transpose of A inverse. Yeah. So these things work very nicely. And in point of fact, the matrices which are invertible do behave very, very nicely. But that's kind of boring. Okay? When we look at some of our later problems, where we're going to use these matrices to solve, we're going to be much more interested in those matrices which have all zero rows, and hence we're going to be interested in those matrices which don't have inverses, right? And those are a little bit more difficult to work with, but still kind of fun, and they create much more enjoyable answers. Okay, make sure you get your homework done for section 2.6 as usual, and I will see you guys next time.